Hello? Would we start?
Yes, Maret, you can start, sure.
Okay. Good morning, all of you. It's an honor and a real pleasure for me to moderate this session with such distinguished scientists. And so just to inform you how to proceed, the question should be asked during the talk by typing in the chat, please. And at the end of the talk, there will be time to questions, 5 time for talks of 30 minutes and longer, and 2 minutes for talk of 50 minutes. So we will start now with the talk of Jaan Einasto. Please, the biasing phenomenon. Thank you. Jaan, please.
Hello, everybody. It's really nice to have this talk. The problem biasing phenomenon is actually relatively old, as old as a study of modern structure of the universe. In early time, roughly 50 years ago or so, only apparent distribution of galaxies was known. Here we see the distribution according to Lick survey, and these early data suggested that the distribution of galaxies is almost random. There are some clusters, some even superclusters, but the general picture is randomness. And this was explained by hierarchical clustering model by Jim Beagles. Now, the same time, Jakob Zeldovich had an idea of how structure could be formed, suggested the pancake theory. But initially it was known how to compare it with observations. And then he asked our team in 1974, can we bring some observational arguments to make selection between different theories? And after some thinking, we understood that all such structures evolve very slowly. And if there exist large-scale structures in the universe, then these must be primordial from the very beginning. And really, first numerical simulations made in the framework of this pancake model, Doroshkevich Shandar in 1976, they show us a picture, but what is seen here. There are some scale structure, clusters, filaments, low-dense regions, but to this time we already had almost ready our data analysis, and what we found is here. The left is distribution on the sky of Zwicky near clusters. We see here regularities is chain of clusters here too, and here is a slice of galaxies. It seems slice of galaxies. We are in the center, and we see also filaments, rich clusters. And what is there are two points important. First, really there exists structure, and second, these voids in galaxy distribution, they are empty. But it was clear from the beginning that gravity, which is a basic force in this case, it can evacuate, it cannot evacuate voids completely. There must be dark mattering voids. that means distribution of dark matter and galaxies of various luminosity is different. And this is a biasing phenomenon. The biasing can be measured and interpreted in various ways. Modern biasing studies are basically devoted to investigation of the formation of galaxies, but we consider here another aspect, how structure is, how the structure looks like, how it can be described in numerical terms. And usually here two approaches are either correlation function or power spectrum, and biasing parameter can be defined either as correlation function divided to correlation function of matter, and the same for the power spectrum. To calculate correlation function in three-dimensional space, distances of galaxies are needed, but it is known that redshifts are distorted by motions, finger of God effect, and contraction of superclusters. And then to avoid these effects, quite often a two-step procedure was applied. First, correlation function was calculated using two-dimensional distribution apparent, and then it was two-dimensional distribution was converted to 3D using Limber equation. This equation assumes that distributions in 2D and 3D are similar. And here are the first results. These three curves are biasing parameter calculated either from correlation or spectral analysis. Here is luminosity of galaxies. We see that it depends on luminosity, and on median luminosity range, the factor B is roughly 1. On the other hand, together with NSAR, we find a method how to calculate theoretically, and we found that the bias parameter should be proportional to the inverse version of the fraction of matter in clustered population. It is clear that the matter can be divided to two types, clustered galaxies and less clustered, this is voids, and this is a biasing factor. And because always less than 1 is clustered, that means B must be greater than 1, and this is the result of our analysis at this time. And here we see differences, and we have a problem. Why these results are different, and find relationship between galaxies and matter distribution. And second, because most of these correlation analyses were based on two-dimensional data, find relations between 2D and 3D correlation function. We apply in the study two simulations. One is a lambda model, our own model, where dark matter particles are known, and the other is Millennium model, where simulated galaxies are known. And we calculate for both correlation functions and power spectra using various limits particle density in this our own model, and galaxy luminosity in millennium model. And what is important, we apply here a new method to calculate correlation functions. It's a density field method. This method is new. Somebody suggested it, and it handles correlation function and the power spectrum in the same way using fast Fourier transformation. Input data are the same, only the analysis is different. In one case, we get a spectrum. In a different way, we get a correlation function. And here is our result for three-dimensional correlation function for our own model and the millennium model. Here is a scale, distance scale. Here is a correlation function amplitude here. The dark black line is for dark matter, and following lines are for simulated galaxy ensembles. They are found so that low density regions, low density particles are excluded, as in real galaxy samples also low density dark matter is diffuse and cannot form galaxies. And here is the same for millennium. Now, how to explain this difference and this increase? Here is a cross-section through the density field. Here is density relative density in relation to the mean density. The blue line is here the original more or less random distribution at the beginning of simulation. A black line shows the cross-section of the density field of dark matter. We see here peaks of high luminosity and high density, and some slower peaks. Most of the field density is very slow. And here in these regions, in these low density regions, galaxies cannot form. The galaxy density field is shown by a red line. And how to interpret this? The power spectrum is calculated. This is square root of this density, relative densities. If density is 0, then this relative density is -1, and the square is 1. In the dark matter field, these density have values roughly maybe 0.5 or so. In galaxy density field, it's always density contrast is -1. This square is 1, and the sum of these cells with these minus or ones is larger. And our result is that this amplitude of the power spectrum and similarly the correlation function is larger, the greater is the fraction of zero density cells. Amplitude of power spectrum and correlation function actually measures the fraction of zero density regions. And here is a summary of the first part of the talk. Amplitude of galaxy power spectrum and correlation function must be always higher than amplitude of power spectrum of the dark matter. And that means bias parameter is always larger than 1. And our own estimate shows that it must be roughly for this L star galaxies roughly 1.8. Now we turn to two-dimensional correlation functions, which were used by many astronomers who studied this problem. We made in this our models, this is our own lambda model and this millennium model, we have a cube. We divided the cube into slices in vertical direction and calculated two-dimensional correlation functions separately for slices. One case is where the whole Z cube is used. In this case, the thickness is the same as the whole cube. It is 512 megaparsecs. When there are two slices, then it's half, and the finest is the whole cube was divided to 2,000 slices. Every one has a very, very thin thickness, and the mean was found. And this is the result. This is for the whole integration. Here is by 2, and so on. And we see that all these amplitudes are less than the 3D case. 3D case is here. And the more negative or slower, the thicker is the slice. And the same using millennium galaxies. The effect is the same. And here it is shown in graphical form. Here is thickness. Here is amplitude measured in no, yes. Measured in central regions, and we see that very smoothly it decreases something. Now, how to explain this? Here is our density field of our model, and we see here slices which are 8 megaparsecs thick, only 8 megaparsecs thick, but in different places here. We see that visible structures are always visible, but they are located on different places. When we stack all together, we see this picture. When we take 1/2, we see here the overlapping of these structures is less, and here this is even less thick, 1/4. Here we see overlapping of these structures even less. And what is important here in very thin slices, it's seen that most of the volume is empty. This calculation shows that roughly 90% of the volume is empty. Only 10% is filled with clustered matter galaxies and so on. Here, a quarter of these low density regions is lost by overlapping. Here is overlapping still larger, very large here. That means this overlapping, the projection effect changes amplitudes of both correlation functions. of this two-dimensional correlation function. And now we look again these results. Here is our own measurement of the correlation function using three-dimensional data, and also power spectrum analysis shows this. And authors who used two-dimensional analysis, they have much lower amplitude. And this is an apparent reason why amplitude here is smaller, because in a two-dimensional density field, this is not taken into account. And here is the second summary. Dominant elements of the wave are clusters and filaments, and voids. Voids fill most of the volume in two-dimensional sheets. They are located in different positions, and by stacking together decrease amplitudes of correlation function. For this reason, correlation amplitudes of 2D slices are always less than amplitudes of 3D correlation function. And it is clear because the structure is different, then 3D field cannot be restored using 2D data only. The 3D data must be used directly. And the final aspect in our talk is fractal properties. Correlation function has one more important information. If we take logarithmic gradient of the function 1 plus correlation function, this is a standard way how to calculate. We see here for our n-body model, here is for Millennium Galaxies. Here on very small scales, up to maybe 2 or 3 megaparsecs, we see the internal structure of halos, dark matter halos. Of course, correlation function integrates over the whole volume, so it is mean, but we see very clearly this dependence at small radius. All gradients have the same value, roughly here, minus 1.5 approximately. This is just the slope, the characteristic slope of the central regions of dark matter halos. When we go further, roughly here, we have the boundary, characteristic boundary of halos, and here in this range, we see already the distribution of galaxies in the wave in general. It also depends on the magnitude limit, and here is the galaxies. The main difference between dark matter field and galaxy field here is in Millennium is that in galaxy data, the internal structure of halos is not so well seen because galaxies don't populate so well halos, and this is a very small difference. But the general trend in large scales is practically the same. And this third summary, effective fractal dimension of the wave is a function of distance. On small distances, it characterizes the distribution in halos clusters, in large scales, in the cosmic wave. And on very large scales, it goes to 0 or factor dimension to 3, because the distribution is roughly homogeneous on large scales. As we see, biasing problem is a surprisingly complex phenomenon, and here theories of galaxy formation meet with studies of the structure of the cosmic web, and this analysis has shown some surprises we didn't expect earlier. Thank you.
Thank you, Professor Einasto. I asked to the speakers about the questions. So this biasing phenomenon is a very interesting phenomenon about the structure, the fractal structure. The correlation dimension function is a function that is determined in the same way in 2D geometry or in 3D. Yeah, is a unique.
Yeah, actually, 2D integrates some important aspects and details are lost. So if we are interested in the structure, we have to use 3D data. Because the real structure, as we have seen in the very beginning, three-dimensional distribution is much more complicated than the apparent two-dimension.
Okay. Other questions? Okay, if not, thank you, Professor Einasto. We can go to the second speaker, Piero Rosati. Piero, you are here.
Yes, can you hear me?
Yes, yes, very well. So the talk is about the cosmography and tests of the LCDM paradigm with a high precision, strong lenses modeling of galaxy clusters. Please, Piero, thank you.
Sorry, it just disappeared. Okay, so first of all, thanks for the opportunity to present this data and these new results. I'm grateful to organizer for that. So let's see. I think there is, we have a reasonably well-established scenario for the formation of galaxy clusters. We know that they form from the highest density peaks in the early universe, and then there is a progressive hierarchical aggregation of dark matter and baryons, which along the way they, in their different phases, hot and cold, they undergo different transformations. We know that at least for the most massive clusters by redshift 2 or so, you know, most of these transformations are already taken place, and it becomes interesting to look at, for example, the structure, the inner structure of these halos, which they form both in their baryonic and dark matter form, and compare them with this scenario. I mean, this is quite say in clusters, since we can observe all the baryons basically, and we can probe the dark matter. And I think clusters are really a good place to start if one wants to study in details the structure of these big halos, okay? And specifically, I mean, we can test, apart from the cosmological importance the cluster have, you know, a field which will be revitalized dramatically in coming years with Rosita and Euclid and so on. But here, I mean, this talk is mostly deal with the structure of these halos, and because lambda CDM makes pretty distinctive predictions on that. You know, we know that there are universal density profiles for dark matter. There's also cosmological hydro simulations make predictions also on the distribution of the baryons, on the inner structure, so the subhalos distribution, the inner slope, for example. And specifically, if we probe the core, we can test also and constrain the collisionless nature of dark matter, and possibly also non-standard gravity theories. So if how do we do that? Well, if you want to, from the GR point of view, as we know, if you want to constrain the mass distribution, you need to probe the space-time curvature of round clusters with the different tracers, either dynamical tracer like stars, galaxy, gas, or you can use photon trajectories. And this is gravitational lensing, which is pretty much the focus of my talk. Okay, and if you're lucky, and then you get to see a transient source going through, being lensed by the galaxy cluster, you can further use the time delay to actually probe the full space-time curvature around clusters. So you need to embark on a pretty ambitious program if you want to model and reproduce in details the density profile of clusters, which in principle goes from 1 kiloparsec to a few megaparsec, and combine the different all these different probes, because they have different sensitivity to different radial range, and they are actually affected by different systematics. But if we're interested in the core of clusters, and this is definitely something of special interest, because the cores are sensitive to dark matter physics, as I just mentioned. They are sensitive to baryonic effects, feedback and back reaction effects. Then we need to turn into strong lensing, which is the only one of these among these methods which actually has an angular resolution. Okay, you can really resolve the inner structure of this halo. This is why we're putting so much emphasis on accurate and precise strong lensing models in recent years. So now we'll describe the transition driven mostly by the data, the quality of the data that we have witnessed over the last few years in modeling, so transition to high precision strong lensing modeling. Once you have that, we show you can really then compare directly the mass maps from these cosmological simulations with the one derived from the lensing data. And you can also, I will show you that once you have these highly precise and accurate models, you can actually see that you can investigate lensing cosmography with clusters, and we'll see that both geometry and expansion rate can be constrained perhaps in a surprising way. And then once that's one of the other drivers for building these high precision models was if you want to use effectively these clusters as the most massive clusters and big lenses as really cosmic telescopes and probe the really high redshift primordial galaxies or primordial star formation size, then you do need to rely on your magnification maps if you want to derive reliably the intrinsic luminosity, star formation rate, stellar masses, sizing, and space densities, and so on. So these are the three. So I will concentrate on these two points in this talk. So what you need to really build this high precision model. So one could say, well, HST data, for sure, HST data are critical, they're beautiful, and they have coordinated programs and a lot of orbits over the last, I would say, 6-7 years have definitely moved this field considerably, but it's not enough. This is something that's never really emphasized. If you really want to make this transition to high precision lens modeling, then you need to have extensive spectroscopy, because you cannot just find the multiple images in these clusters via photometric ratios, and you cannot afford not to have spectroscopic ratios. And so integral field units, and particularly MUs on the VLT, which we have been using extensively over the last years, is really critical in this case, because you have the full spectroscopy of the inner cores of clusters, and you can find blindly multiple images. You can measure and the clustered galaxy. You can really identify spectroscopically the clustered galaxies, and you can even use internal kinematics of clustered galaxies to add extra constraints on the mass, as I will show of the subhalos. And so this is until recently, is probably one of the field which had the best constraints. And so when I talk about high precision, usually I refer to to measure the precision and accuracy of models. Usually a figure of merit is used, which is simply the RMS scatter between the observed positions of the multiple images and the predicted positions of the multiple images from by the model. So if until a few years ago, this scatter was around a couple of arc seconds, and this is definitely not enough to do the kind of test which I will show today. So obviously, the more you have, the more images, multiple images you have, the better is the constraint, more resolution you have, more robust, less systematics there are. But again, you need spectroscopic information. So there's a number of data sets and surveys which have been critical for this development over the last years. CLASH and the follow-up, the spectroscopic follow-up, which we conducted, is one of these. Then in the wake of CLASH, the Hubble Frontier Fields program with Hubble looked in great details at 6 of these massive clusters. And then, as I said, we launched first a VLT spectroscopy for VMOS, and then we complementing the core of MUSE. And these are the light cones of all the spectroscopically identified galaxy in each of these 12 cluster field. In red, you can see the clustered galaxies, and you see there's a lot of structure, as we know, along the line of sight, and it's important to know, again, if you want to model precisely the cluster model, the lens. And so this, for example, it's one of the fields. You see you have these light cones. You combine again VMOS, a large field, 2 or 3 megaparsec, and then you have a pencil beam probe, spectroscopic probe with MUSE in the core, and you can easily disentangle the clustered galaxy from the overwhelming field galaxy in this way. And this is all crucial for what we show. So just a word on the methodology of how to model these clusters. Here we're using parametric models. So typically you model the potential, the cluster potential with a combination of cluster diffuse halos, so cluster scale halos, and typically you use pseudo-isothermal ellipsoid, and then you have to add the subhalos. Okay, so you have to have other possible pseudo ellipsoids to model all the subhalos, which are associated to clustered galaxies. And then, since in clusters, most of the baryons are in the gas, and since we do have we do have information on the gas distribution and the gas mass from Chandra data. In this case, if we have Chandra data, which we have from most of these clusters, it's good to include that too. So you have already a good representation of most of the diffuse baryons. Then, again, if you have access to internal velocity dispersions of clustered galaxies, you have an extra very important constraints, because at that point you can sort of construct the Fabre-Jackson relation of your clustered galaxy and sort of set the normalization of the light versus mass relation, which is usually taken free in models. So again, this is an extra ingredient which has been explored and developed by Piero Berganini in his thesis last year, which is very important for what I will describe. And then obviously you need to minimize a chi-square, which is that basically just the difference between the observed positions and of the multiple images and the ones predicted by the model. Then at the end of this, you get these mass maps, and obviously you get also the magnification maps, which are very useful if you want to, as I said, if you want to use these clusters as cosmic telescopes. This is, I would say, is definitely the best data set, which will all be published in a few weeks, at least submit in a few weeks. where basically we have used MUSE to have a very deep 17 hours pointing in a piece of this max 0416 cluster version 0.4. And in this case, really, there was an amazing number of extra multiple images that we find. Most of these are just line emitters, extremely faint, you know, down to 29 magnitude, which you can detect in MUSE. And so in this case, you can run your model. You can afford to have 30 parameters, free parameters, because you have, in the end of the day, 230 in this case, independent constraints. And so in this case, you reach a RMS difference, so a positional difference between observed and predicted images of only 0.4 second, which is quite amazing if you think that now we're dealing with 180 spectroscopically multiple images, which is by far the largest number of multiple images. So this is really a good test data set for doing all the physics I described to you. And so let's start just as an example, because I cannot cover the whole thing we can do with this. Let's start with, again, quantifying the internal substructure of cluster halos and compare them with the high resolution cosmological simulations. So obviously you need to extract from the simulation cluster in the same mass range or the same radial range. You need to match your observed data sets with your simulated data sets as much as possible. Once you do that, you can then, for example, look at the subhalo mass function, whose proxy is the velocity function, which is shown here to the left. You see here in these three colors, these are the velocity functions derived from the measure sigma plus lensing modeling. And so basically the number of these halos is a function of, in this case, circular velocity. Okay, the circular velocity is basically the square root of GM over R, as we know, and so it's a good proxy actually of the compactness of these halos, of these subhalos. Now, the first results already in 2015, which, you know, we were cautious at that time, we find that there was a big mismatch between these observed velocity functions and the one derived from the simulations. As if, you know, then for further studies has shown that at the same mass, it looks like the circular velocity of the observed halos is higher than the simulated halos, as if, you know, as if the lensing models point to more compact subhalos around the cluster galaxy than what is predicted from the simulation. To the right, you see the same thing. All the color points, all color dots are there from the simulations. Is the distribution of circular velocity as a function of subhalo masses, and this is the observed relation. You see there is this factor 2 mismatch. But, you know, then if you look at actually the subhalo mass function, that's not too far from the observation. So really, what is the tension here that we found has to do with the internal substructure, okay, now of these subhalos. Now, there is another metrics that we've been using, and with a study that Massimo Meneghetti has led, is a different metrics which look at the same problem. And the metrics is, you know, you can sort of count how many galaxy scale systems you find in this cluster. Often this cluster, since you have this huge boost from the cluster field, the cluster potential, then you tend to find extra strong lensing systems, which are like Einstein rings and little multiple images around cluster galaxy. We call these galaxy strong lensing events. You see in this case these three examples. So at that point, you can compute the probability of having this strong lensing, galaxy scale strong lensing events simply by going and look at modeling again the lens. From the lens model, you can look at all the caustics associated with the cluster galaxies on the source field, on the source plane, okay? And these secondary caustics, if you sum the area of the secondary caustic and you take the ratio with the total area that you have access to on the source field, this gives you the probability, basically a cross-section for these galaxy strong lensing events. And then you can compare the ones from the observation with the one from the simulations, and you immediately see qualitatively, and obviously you quantify this, that the number and especially the sizes of these secondary caustics in the simulation are much smaller. If the caustics are smaller, the probability to have to generate these galaxy events, strong lens events, is much lower. In fact, if we then look at a number, we have a sample of 10 clusters with good lens models, and you look at this probability, which you can turn into a number of events by simply placing in the back a population of galaxies, of source galaxies, which usually is taken from the frontier, from the deep fields. But then you can compare the number of these strong lensing events on the small scale with the one predicted from the simulation. There is a factor, there is a factor of 10 difference. So here is more dramatic, the effect, but this physical result is the same. The internal structure, again, mapped by the circular velocity, if you want, and even the rate of distribution of the subhalos in the simulation is different from the real clusters. In other words, in the real clusters, these subhalos appear to be more compact and also more concentrated in the cluster center, and this produces this excess of events. And so there is a subhalo, is confirmed now, there is a subhalo compactness problem, which really we don't know what the reason is. It could be numerical artifacts. We have investigated a lot of these. It could be perhaps the dynamical processes which lead to the disruption and formation of cluster galaxies. They're not all captured. Perhaps there are deeper problems with LCDM, who knows? Or there is simply a poor understanding of the interplay between baryons, and dark matter, all those back reaction effects. So all this will be actually, coincidentally, it will come out tomorrow on a science paper led by Massimo, and there will also be a number of press releases coming out in a few hours. Now, let's turn to the intercosmography. This was perhaps a big surprise, but I think it's quite interesting. So we know that if you're lucky and you have a variable transient source in the back of a cluster, and these sources are multiply lensed, then you can use the time delay, between these two events to actually measure H0. I mean, the reason is that this time delay is given by the potential, the Fermat potential, to which, as you know, there are two terms. One is due to the geometrical difference delay, and the other one is due to the Shapiro delay. And then you can define this time delay distance, which is, since it's the ratio of 3 angular diameter distances, basically goes like H0 to the -1 times the dependence from cosmology of the angular diameter distance. So, in principle, then, if you can measure this difference, you can constrain H0. We'll come back in a second. But in clusters, you have an additional advantage that you have many sources which are multiple images at different redshifts. So in this case, you can actually use another probe, which is the ratio of the angular diameter distances. And here, in this case, H0 cancels out, but you are left with something which is, again, sensitive to the underlying geometry, and with obviously a different function from the one below above. So in principle, then, if, and this is a big if, the mass distribution, so the lensing potential is actually modeled, a measurement of the time delay between the multiple images can constrain the Hubble constant, and potentially also the underlying geometry if you have a lot of these sources at different redshift which are multiply lensed. And so this was at least on the galaxy scale level. This has been exploited by the Optical project, who has been monitoring multiply lensed quasars by galaxies, by seeing early type galaxies, and measuring the time delay. And this has led to a number of measurements of H0. You can see here on the left, this is the latest release. You see these are the single measurement of 6 lenses. And then if you combine the measurement of 6 lenses, you go down to a measurement which is around 2% accurate. And this seems to be becoming, and it's actually consistent with the late universe measurements, the one coming from supernovae, from shoes, and so on. And so as we know how important is this because of this tension which we have created compared to the H0 measure from CMB. So Refsdal is the one who he wrote this seminal paper in '64, where he said, if one day we will find a supernova multi-valence by, in this case, a galaxy, then we'll have a chance to measure H0. But clearly, people were quite skeptical in doing this on clusters, because they would say, well, cluster masses, the mass of clusters is too complicated. You will never get to separate the mass, the obvious degeneracy that you have between mass distribution and time delays and geometry. Well, as I told you, however, with this new highly precise strong lensing model, situation is changing. Fortunately, in 2014, there was the first opportunity to do this. There was this great, perhaps once in a lifetime opportunity, where in one of the clusters we have been studying with Mark Postman, who led the survey at that time, by comparing the new image with an old image, it was clear that there was a supernova that had gone off in this phase-on spiral galaxy, which is in the back of these clusters at redshift 0.54. And you see that this spiral galaxy is imaged 3 times, one here in the center where the supernova was actually then further lensed by a cluster galaxy producing this Einstein cross, the typical configuration. But then there is another image in the core, completely shredded by the strong potential in the core, and a more normal, if you want, less disturbed image in the outskirts. Okay, so at that time there was no spectroscopy for this cluster. That was the problem. But it was already clear that this image somehow belonged to the past, and the one where the supernova had been discovered, obviously, when it was discovered in 2004, then already the first lens models suggested that this image, this supernova, would have been reappeared somehow a year, 2 years, it wasn't clear at that time, later in this central image, okay, where obviously the Shapiro delay is the strongest, so you do expect being the last the photons are the last to arrive. Okay, and so this challenge was launched. It was really a once-in-a-lifetime opportunity to make blind predictions, because you can say when you have so many parameters, you can get things to work all the time. But in this case, there was a number of groups were supposed to deliver their prediction on when this supernova would reappear. Okay, and to make the story short, the supernova you see here, this is the supernova, the 4 images, which reached the peak in April 2015. And when this was sort of disappearing after a year, indeed, more or less, the second image in the central, the second image of the supernova, the reappearance of the supernova in the central image occurred. Okay, so at that point, we compared the different predictions, and we were quite pleased that our model, led by Claudio Grillo, was the one which performed the best, because it was able to predict both the prediction, both the positions within 0.4 arcsecond and the time, because you get to get the 2 things right at the same time. So the banana here is is basically the observation. So when the supernova was observed, at that point you can sort of plot from the magnitude of the supernova and the time and the appearance time epoch, you can sort of constrain in this space. This is the banana constraint by the observation. These are all the models, and so the fact that we
there are 5 minutes.
Okay,
5 minutes left.
Sounds good. Okay, so at that point we were quite pleased, because it means, this is wasn't supposed to be that way. So if we're able to predict quite precisely, and now we'll go more the appearance of the supernova and the time delay, it means basically that you are able to constrain not only the potential, which gives you the time delays, but also the second derivative, the first derivative of the potential, which is the position, and the second derivative potential, which gives you the magnification. Okay, so basically when the supernova will come bright enough to be observed with HSC. And again, this was all possible because we launched with Claudio, we launched an extensive spectroscopy program with the Muse, and we gave to the community, we distributed to the community all the multiple images, spectroscopically confirmed multiple images, and so they could actually run these models with this high quality data set. So obviously, somehow this was, we were encouraged by this. We thought, okay, let's try then to measure H0, okay? And in this case, we're talking about 89 multiple images. However, the great advantage here, perhaps you want the fortune of this situation, is that all these star-forming knots in the host, in the spiral galaxy which hosts the supernova, all these star-forming knots can be identified, again, using the MUSE data in the other images. So the star-forming knots act as extra constraints, exactly where you want them, because where the potential needs to be constrained the best. And so we've been, so the measurement, the actual measurement of the delay should be released any time. It's not been released by Pat Kelly and collaborators yet. So we used, the original estimate of the time delay and a number of time delays. Then we know, after all, the H0 scales inversely with the time delay to actually make predictions, blind predictions of what the H0 accuracy would be. And here the model is very accurate. Not only you get 0.26 arc-second RMS, but look at the image. These are the data to the left. This is the model, and this is the normalized residuals invariance on the image. And you see that the surface brightness distribution is reproduced extremely well by the model. So at that time, we did run the experiment, okay? And to our great surprise, it appeared that we were able, especially now with the projects, again, we don't know what the time delay is, so I cannot give you our measurement of H0, but I can give you the accuracy and the precision, because we investigated the systematics extensively, assuming a 1.7% measurement of the time delay, which Pat Kelly has anticipated. And so in this case, you see you get an H0 measurement with 5 to 6% accuracy, including systematics. Okay, that's important. Now, if you compare it to the holy cow, you see the difference. The most important thing to stress here, that there are absolutely no priors on all the other parameters. Basically, we assume omega matter anything from flat from 0 to 1, omega lambda from 0 to 1, and so there are no prior whatsoever. Unlike in the case of the Holy Cow project, because in that case they have quasars at just one redshift, so they are not sensitive on the underlying cosmology. So this is why they have to assume a strong prior on omega matter. But you see already that the single measurement is comparable to the one on Holy Cow. But then we at that point you can start investigating even other models. You can introduce models with W, with the equation of state parameter W of dark energy density. And interestingly enough, you can see that the model is extremely stable. Again, without no priors whatsoever, you can say H0, omega matter, omega lambda, and W. There are no other experiments who can do this, as you know. And you see that in this case, the advantage compared to Holy Cow is quite dramatic, because obviously Holy Cow does have this degeneracy with W. So just to finish, this our forecast. Again, we need to have the final measurement to really turn this into a real measurement. Already, if you compare, even if you use Planck and Planck BAO, of W versus H0, you see that in this case, Refstal alone is able to actually constrain this quite well. And this is also true for omega matter and the curvature. Even, this results are extremely stable. So to summarize, the ability to run these highly precise lens models have opened a number of opportunities. You can really compare now the mass maps with the simulation, and you can separate. I don't have time to say that the baryons from the dark matter. Also look at the inner core of this cluster, which much more confidence. And I told you about this mismatch that we found in the mass distribution of the subhalos. and we still don't know whether this is something fundamental has to do with our poor understanding of how cluster galaxies and their hosting halos form in the near cluster. But then again, there is this great opportunity when we will find more Repstar-like events, perhaps with LSST, not Euclid, but LSST, and then you can rerun the experiment. And again, there is much more, to do now with these models, is plotting these clusters gravitational telescopes to explore primordial star-forming sites. I'll stop here.
Okay, thank you, Piero. We have the question of Gregory Vereshakin and Su Shisheng. Please, Gregory, could you ask yourself the question?
Okay, let me try. Hello, can you hear me?
Yes.
Okay.
Yes.
The question is really, first of all, congratulations, really fantastic talk. I wonder if this subcolor compactness problem you find be somewhat related to the missing satellite problem of lambda CDM.
Yeah, no, actually, there are two different things because, as you well know, the missing satellite problem is really segregated on the faint and mass of the mass function of the scalars. And we were talking about velocities or less of 60 kilometers per second. Here instead, we are talking about the medium to high mass end of the subbelow mass function above 100 kilometers per second. So the two things are, I know that they look similar, but actually they are unrelated. And this sort of, if really halos are more compact, even on the faint end of the mass function, it would actually make this missing satellite problem even worse. So yeah, they're not related, or perhaps we don't understand whether they are related.
Thank you.
Shisheng, please summarize your question to the speaker. Shisheng, can you hear me?
Oh, yes, I answered several questions even before the speaker present his results. So first question is not relevant because he answered. So my question now, let's summarize is, does this H0 measurement is strong dependent model, number one? Number two, I see your result of H0 is in tension with the result from Planck.
Okay, so the last session, because it's easier. No, it's not, because the error bar at this point, we're still not in the 2% regime. We're talking about just one system, and the error bar, as I said, is between 5 and 6%. So if this means that basically the Planck results, you can see it from this picture here, from the red dashed line, the Planck results is actually in this case consistent at between 1 to 2 sigma, perhaps 2 sigma. So again, we need to have other of these systems as the Olicao project is done, and then combine more measurements to really shrink the error down to 2%. But this is all about systematics, and we discussed about this. The great thing about the clusters cosmography, there are a lot of the systematics which affect cluster galaxy cosmography, like the mass degeneracy, for example. Again, we have demonstrated this in the paper in 2020. They're strongly reduced by the fact that there are not just one source redshift, but the several different source redshifts, and this sort of cancels out the possible effect due to mass degeneracy. So the mass model, it's hard to improve the mass model. So this 5% error basically comes mostly from the uncertainty on the model, because you would need perhaps another 100 multiple images to further improve this, which we don't have at this point.
Last question is this data, what's redshift about this measurement?
The measure, so right, correct. The supernova is a redshift 1.5, okay? So, and the clusters are redshift 0.54. So it's a measurement basically around redshift 1.5. That's the answer. So again, late universe measurement if you want to. Okay.
Okay. Thank you, Piero.
Thanks.
Thank you for your very interesting speech. And
Any
then-
chance to see a GRB lensed?
We are making predictions with Cristiano Guidorsi here and Tommasio. We are trying to make predictions on that. It's yes, of course, it is possible. Even gravitational waves can be lensed.
Well, forget about, but GRB are real.
GRB, yes, they can be lensed. We are making forecasts on what is especially with Theseus, for example, what would be the probability of having a GRB lensed when we have a lot of GRB.
Yes, we have been very impressed by the talk of Lorenzo on previous days, and it looked very, very promising. And it will be very interesting to see if from Rosita we can have some information. Okay? Beautiful talk. Beautiful talk.
Yes.
Thank you.
The first speaker, Joseph Silk, the Future of Cosmology. Please. Thank you.
Let's see, click on the microphone. How's that? Hello?
Yes, we can hear you.
Can you hear me? Good, very good. Sorry about that. Okay, it's a great pleasure to be here, virtually, of course, and I thank your invitation. I'm going to really tell you a story about where we may well be going in cosmology if we want to make real future advances in this field. So let's just reflect a little bit. Cosmology has made immense progress in the years since I've been in this field, which is well almost 50 years now. And I was lucky as a graduate student to have run into Jakov Zeldovich. He actually insisted on meeting me in a swimming pool and demonstrated his greatly superior athletic skills compared to mine, apart from occasionally discussing science in between the odd stroke. And so Zeldovich and Jim Peebles are the two great pioneers of what we call physical cosmology. And it is amazing over these few decades how the parameter uncertainties, which were enormous in the 1970s, orders of magnitude really, we now discuss 1% accuracy in cosmology. So we've entered the era of precision cosmology, but what we have to bear in mind is this may not necessarily mean accuracy. And that is our big debate at the moment. And so the question is, where should we go next to try to really pin down better our fundamental cosmological model? Okay, so my starting point really is that inflation, which has been this wonderful framework really for understanding the universe, has still a understood beginning. And we would like to improve the verification of this. So how do we go about that? Well, we have a number of measurements that all support inflation. The flatness of space, the size of the universe, the density fluctuations, all of these are beautifully consistent with this class of theories. But we have we need to go to do more than this. So there are predictions. And so how do we attack some of these? Well, dark matter is one major prediction. We have no detection. Dark energy is an inferred prediction to balance out the universe, really. It must be present. We have no understanding of it. There is a gravity wave background produced by inflation, characterized by the tensor to scalar radio. The searches are underway to look for this, but there's no guarantee that we'll find it. A galaxy formation, we want to test the fact that it starts from small scales, hierarchically builds up to larger scales, and we're having a hard time doing that. And finally, primordial non Gaussianity may be a wonderful window on the beginning. And that's the deviations in Gaussianity from the temperature fluctuations on the sky. And now I want to discuss very briefly some of these issues and where we will go next, maybe to resolve the most important of them. Okay, well, dark matter, briefly. Today, we have no success deep underground in looking for dark matter scatter particles, weakly acting particle scattering of protons. Let's see, thank you. We are looking for annihilation products from gamma rays from these weakly acting candidates produced thermally in many models in the early universe. They should give a very weak signature today. If they're typically GeV scale mass, we should be seeing gamma rays. We have not seen any indication of these, either from the center of the galaxy or from nearby laboratories, dwarf galaxies. And then finally, our direct searches in accelerators have not gotten very far in looking for missing jet events. The problem is there's this vast parameter space to explore. We've just really skimmed the surface in one or two areas, and we have a long way to go. So it's hard to be confident that in the next decades we'll be making progress there. I am simply pessimistic about remarkable to see how far we've gone in 2 decades. You can see on the left where we were at around the time of the discovery from supernova of the acceleration of the universe. And this is where we are today. We've greatly zeroed in to tiny scales, 1%, few percent accuracy, but we still are pinned down at the W minus 1, P equals minus rho, the standard equation of state with a cosmological constant. We haven't, and there's no indication we're ever going to move away from that as we improve our accuracy. Wouldn't be wonderful if we could, but there's no really theoretical groundswell that we should be finding something. Microwave background. Again, incredible progress from the early days. We've built up from handfuls of detectors in the WMAP satellite, many more in the Planck satellite, now measuring fluctuations on the sky, these beautiful maps of temperature fluctuations at the microkelvin level. But to really get, which tells us all about the density fluctuations that gave rise to large-scale structure. But what we'd like to do to ultimately test our inflation theory is measure the tensor to scalar ratio. And that means you have to do something like 1,000 times better than we currently are doing, looking at the nano-K level. So there are plans underfoot to do this, basically by scaling up detectors. 1,000 detectors in space on Lightbird projected for launch in 2027. That'll get us down orders of magnitude below where we are now with our current upper limits. Maybe even better if we can solve the foreground problems from terrestrial experiments, using up to 500,000 detectors and getting more sensitivity. Of course, detectors on the ground, not, one needs many more of them for anyone in space, but nevertheless, we are projecting to get down to scalar to tensor ratios of 10 to the minus 4, maybe, if all goes well in the next few years. The trouble is, there is no definite prediction because the reheating post-inflation is so uncertain. The tensor to scalar ratio could be much smaller and well away from the scope of these experiments. So that's why I put a big question mark on my prediction there. There's no guarantee of a signal. This doesn't mean to say we shouldn't be trying our very, very best to improve our limits, but what can we expect more rigorously? Well, here is one way to consider going, and this is to go to largely unexplored territory in cosmology, and this is the Dark Ages. So if you can now exceed objects from which galaxies form, the clouds, we believe the typical clouds coming together within which baryons could cool were millions of solar masses, and these were the seeds of early galaxy formation to assemble those baryons together. Then if we can ever capture those initial clouds, there are so many of them, roughly speaking, 1 million per big galaxy, that you suddenly can increase the number of modes on the sky that you could look for. So what do I mean by this? Well, in the microwave background, you're limited by the number of pixels on the sky of order 1 million. And you know, one of the square root of 1 million gives you your limiting accuracy. The push is on to go to large-scale structure at redshifts of 1 or even beyond, where with surveys of billion galaxy redshifts, you can study the power spectrum from baryon acoustic oscillations, etc., and increase your accuracy, most likely by another factor of 10, so going from 0.1% to 100%. But this is perhaps not as far as we'd like to go if we really want to capture a signal from the beginning. And the ultimate experiment will be to use 21 centimeter, where you can look at these cold building blocks and study those first clouds and their distribution by a 21 centimeter absorption. And now you suddenly have a Gaussian modes, 100 million in the optical galaxies, up to maybe 1 trillion modes at 20 centimeters. And it gets even better because of the accuracy of the 21 centimeter signal, you can do tomography and slice up the universe and get even more. So but this is going to be very tricky because we're looking at very large redshifts and the redshifted. But the idea would be to probe what is perhaps the most robust prediction of inflation, which is primordial non Gaussianity. And so I will say a little bit more about that. Okay, so again, to summarize, we have pixel type limits coming from any CMB experiment by definition, because you run to small scale damping after a few million pixels on the sky maybe. With galaxies, we can boost this number of degrees of freedom on the sky. But with the first clouds, we can do so much better. And so you can see these how these building blocks early on the left there in this cartoon, there are many of them, and that's why increased number of modes. At the bottom, you see my sketch of the Dark Ages, but let's just look at another way to look at this. So as I go to higher and higher redshift from left to right, I, of course, go through, and this is the spin temperature of atomic hydrogen, I go through the reionization epoch. There was an early epoch when, before which there was hydrogen epoch, when there was Lyman alpha photons produced by star formation, etc., which effectively couples gives you spin temperature predictions. But what is more interesting is when I get beyond the first stars, way, way back, there's nothing there. That is the Dark Ages. Then the gas, which is on an adiabat and is different from the radiation, is slightly colder and can be seen against the backdrop of the microwave background. So that is the hope. That's the great hope, to catch this Dark Ages signal. The trouble is, it's a very, very weak signal, and it's going to be ferocious to have to deal with foregrounds. From radio foregrounds from the Earth, basically, and even other regions. One has to think of clever ways to do this. Well, the first thing you want to do, because if you want to go to redshift, let's say which is sort of the sweet spot for much of this, is that you have, before any stars had formed, and where there's the largest difference between the spin temperature of the adiabatic gas and the CMB, then you are looking at something like 30 megahertz. And the Earth is not a great place to do radio astronomy at this frequency because of terrestrial backgrounds. So what you want to go to do from radar and many other things, communications, your cell phones, whatever. So the far side of the moon is a great place. It's the most radio quiet environment in the entire inner solar system. We are developing ideas to go to the moon. I'll come to those at the end. One schematic idea is to have a huge interrometer of many thousand, millions even of dipoles spread over the surface in a flattish region. It doesn't have to be very flat because we're talking about looking at wavelengths of 10 meters, so we can deal with rocks and things. And then these dipoles will be connected to give you an interferometer. Typical numbers are that if you want to probe redshift 50, which is sort of the sweet spot to get the optimal signal from the backdrop of the CMB and the slightly colder gas in front, then you're looking at 10-meter wavelength. It means that your effective resolution to try to see signatures of any of these clouds would be roughly 10 or 100 times what we're doing with the CMB, but that's all fine. You can get down to wave numbers of 10 inverse megaparsecs, that's dwarf galaxy-ish. Your optimal array would have to be hundreds of kilometers across, and you need millions of dipoles, and you're looking for a 10 milli-K signal in a bright foreground of 1,000 Kelvin. Now, that sounds crazy, but remember, with the CMB, we went through this process going from 3-degree initial discovery down to microkelvin, and in the future, maybe nanokelvin scale fluctuations. And we shouldn't be scared about having vast numbers of dipoles because we're building these on the Earth in, for example, a projection of the SKA at low frequency. So the technology is pretty much there. We just have to think of clever ways to do this on the moon. So the future of cosmology then, I would say, what are we going to do with this? Well, what we're going to do is go for primordial non Gaussianity, because that is basically a generic prediction, a reasonably generic prediction for inflation. And so there is, this was originally a conjecture by Olga Sazhina. It's been looked at quite a bit since, but this shouldn't be too far off. People debate the details a bit still, depending on the exactly type of non-Gaussian you want to look for. But it's of order something like the modulus of the scalar index -1. That's the expected level. The scalar index of the fluctuations is roughly 0.96. So you're looking at an FNL of about 0.01 thereabouts, a tiny, tiny deviation compared to the numbers we have present, which are upper limits typically of order 10 from the CMB. We project that as you increase your numbers of pixels on the sky, you'll be able to do 10 times better with galaxy surveys, but you'll never do better than of order 1 with your 10 to the 8th degrees of freedom. However, if we unlock the 21 centimeter dark ages secret, that means we can suddenly increase our number of modes available by a huge factor. We can suddenly get down to the range that we need to explore this new goal, which is by far the most robust expectation so far we have for inflation, even though it may not be completely guaranteed in all models. So that is the backdrop for cosmology. I'll just say a few words about other things one would want to do on the moon. It's ideal for infrared astronomy and for microwave background spectroscopy, both really important goals for cosmology. Here, for example, you can see some dark craters near the South Pole. That's a particularly interesting place to go because these craters are huge. They contain, some of them contain ice inside, and they're so deep, they're permanently dark, and their rims are so high that they actually, being near the poles, are almost perpetually bathed in sunlight. So you have solar power and everything. So they're great places to build telescopes and do other types of cosmology too. And this probably will happen at some point. Just to show you where there's even evidence of water, ice traces in these craters. That they're a great place to explore. There will be a primary target of exploration. So here then are an example of the sort of telescope you could build in one of these South Pole cold, dark craters. It would be an Arecibo type interferometer with many, many mirror segments, infrared segments. And you can imagine building having a huge, huge aperture, 5 kilometers or more, resolutions of tens of microseconds. You could resolve the nearest planetary systems. This is obviously a simulation of what the TRAPPIST-1 system might look like, exoplanets. That would be quite amazing too. And you could look for the first stars. Again, this is the resolution you would have, you would need to get the predictions of, the first star clusters or whatever, 20 in the early universe. Again, a great advance in cosmology if we could ever do that. And then my final comment on doing spectroscopy. So the moon would be an incredible sight in one of these dark craters. 30 Kelvin is the sort of temperature you find. They're permanent darkness, amazing. So why not build a Fourier transform spectrometer there with a telescope to look for the mu distortion? So you heard from Jens Kluber in an earlier talk about the reasons for doing this, looking for this mu distortion. It's a great signal of the early universe that the phi-RAS limit is quite poor. It's right now, it's for the mu distortion, it's about 10 to the minus 4. One has to do much, much better to do. For example, if you want to look for the structures, the seeds of galaxy formation, these are the dwarf galaxies which formed into the big things. They will all have fluctuations in cold dark matter, the standard model that dissipate away. But this dissipation gives you a heating signal, a mu signal, which is set 3 orders of magnitude lower than the upper limit from the phi-RAS experiment. And if you want to do the ultimate thing, which is look for the recombination lines of hydrogen and helium in the very early universe, you've got to do slightly better. And this will be an amazing way of pushing our horizon of cosmology back to redshift 1000 to actually see the physics of recombination. And this will mean going up from the current concept, which is more or less dominated by a telescope called PIXIA, which has never been funded, a 55 centimeter telescope. It couldn't quite get to the desired level, but the new ideas using the moon would have a Fourier transform spectrometer on a 5 or 10 meter class telescope with a number of detectors, and that would be enough to get you to this level. So this could be the future, building spectrometers on the moon, building arrays on the moon. Now, this is all incredibly expensive. And so the question we have to ask finally is this just a dream, or is there any realistic hope that somebody might be willing to pay for this? Well, the answer is we should be optimistic, because here we are. We're now discussing internationally going to the moon and doing science on there, initially putting people on the moon. The US has a plan in actually only 4 years' time to get the next people on the moon. We're discussing liftoff capacity for the moon, what one might do on the moon. There's major interest around the world in this from the major space agencies. The US is very interested, obviously, in certain aspects of exploring the moon. Commercial activities are important. Touristic activities are thought to be important as well when we actually do start getting landings on the moon. The European Space Boss, head of ESA, says this is the time to start designing a moon village. Its aims would include mining and tourism. But you can imagine these things are incredibly expensive. Other space powers involved too, and other activities involved too. For example, Amazon is developing, Jeff Bezos is developing his own launchers, and which is to extend the Amazon concept to the moon. the current US presence is limited. It's
Hey, Joe, the audio is cut off.
lunar aspects of other things that won't be doing, tourism, mining, and fuel. And so there's immense interest in landing the first woman on the moon by 2024. That's been announced by both as an option by the US and also by the Space Agency. And they are very planning for exploitation of the moon. And so just say that, why not outside of the moon, away from much of this activity? Imagine our low frequency interferometer array, which would explore the dark ages in the craters, in a crater or two near the South Pole, and usually cold and dark, perpetually dark, with rims that have solar power. Yes, one could build telescopes too. So all of these, I think, are incredibly exciting projects. The time scale, well, 30 years maybe is what we're estimating right now to be back on the moon long before then. Thank you.
Okay, thank you for your very interesting presentation. And I asked to Jens Cuba to ask the question. Please, Jens.
Oh yeah, Joe, you were mentioning that the surface that you can accommodate for rocks, and it doesn't need to be that flat. But I assume that if you know the terrain well, you can probably model even all of that, right? So you don't need to rely on having a very flat surface, isn't that right?
Yeah, that's right. The real worry is actually the tiny particles, the dust, the lunar dust, because one doesn't know quite how corrosive that might be to building some of these structures. So people are thinking of clever ways to try to handle that. And again, it's interesting, lunar dust settles to, at night it settles down, it's electrostatically charged. And so it probably will not interfere too much with astronomy, but all of this is being studied now.
Yeah, great, thanks a lot.
Okay, thank you. For inflation, there are new perspectives for verification.
Yes, so I think, one of the most exciting goals to probe inflation is to detect evidence of primordial non Gaussianity, as this is generic to many models of inflation. Unfortunately, the signal is typically quadratic in the temperature fluctuations of that order, and so it's really, really difficult to get a number on. And the ultimate limitation is modes on the sky. The more modes you have that contain a signal, then you have to work your way down to this level of 1.10 to the fourth, which means many, many modes basically. And so I think if we ever want to get there, by far our best chance will be dark ages, although there are many obstacles to overcome, because that really is a great way to get the precision in principle.
Okay, thank you.
Well, very beautiful talk. But this idea of looking at the dark ages is really very exciting. Of course, since the work of Fermi, we know that at the beginning there was hydrogen and helium only. But now we are approaching from the other side with the GRB. For example, we have reached the first GRB at z=9. And this is really extremely interesting because it means that a binary with a neutron star and a evolved star was already present as Z=9. Therefore, to look inside the dark ages is really a duty at the moment, and to reach as far as possible to understand.
Yes, I completely agree, and yeah.
This limit.
So the sweet spot, sure. So the sweet spot for looking is, where it's really dark, that is long before the first stars form, redshift 50, and that's what makes it so difficult. But it's a new unexplored horizon to look for that so far we're just dabbling in. There are hints of something there so far from the ITERS experiment, but we have to go to higher redshift and confirm that experiment, etc., to make progress. And that's going to happen. It's inevitable. It's the new horizon for cosmology, I think.
But Joe, I would like to stress the point that with the GRB at Z=9, you must have neutron star, you must have evolved star which undergoes supernova. Therefore, there is something which we have absolutely to understand quick at Z=50 or so, how this can have happened.
Well, yeah, no, I agree. Stars are there. They're absolutely, the first visible things we can expect to see in emission. But the dark ages take us back to before the first stars.
Well,
most likely, that's the most primitive info you can hope for.
This is the thing we have to understand properly. We need data. And I fully agree with your presentation to give emphasis to this new field. And the idea of the moon also is very exciting.
Okay, thank you, Joe. And then
thank you, everybody.
Thank you very much. So now the next speaker, Olga Sazhina, optical analysis of a CMB cosmic string candidate. Please.
Could you be so kind to switch on my slides? Because I can't manage myself. Okay. Do you hear me? Do you hear
yes,
me?
All good.
Yes, we do. Yes.
Okay, okay. Thank you very much to invite me to present a talk on the conference, and special thanks to Professor Maret Einasto for her kind agreement to swap the time of our talks. Okay, I would like to present the preliminary results of our group in search for cosmic strings. Our strategy is to search for individual cosmic strings. Next slide, please. I will focus on the following main points. Cosmic strings in astronomy, two main methods of cosmic string search, cosmic string current status in observational cosmology, possible observational cosmic string parameters, cosmic string candidates in CMB data, search for gravitational lensing events along our cosmic string candidate, number one, the statistical excess of the density of gravitational lens pairs in the field of this candidate, and statistical proof of the presence of the cosmic strings as our preliminary results, and also conclusions and future research. Next slide, please. So, cosmic string are one-dimensional objects of the cosmological scales predicted by theory, but has not been found yet. These objects may be topologically entities, which forms according to the Kibble mechanism. They could be endless or infinite and in form of closed loops. They can form as a result of phase transitions in the vacuum stage of expansion and cooling of the early universe. Cosmic strings also come in form, could come in form of hybrid topological and field configurations. It's a very promising model, and so we can search for cosmic string with monopoles on its end and conglomerates of such elements, so-called necklaces. And the also a very interesting possibility for cosmic strings as absolutely non-topological strings which could form from superstring theories, so-called fundamental cosmic strings. One moment, please. I'll discuss briefly the geometrical properties of such a string. So without any string, our universe is flat, but in presence of cosmic string, we will have conical space-time. The metric will be Minkowskian in all points except the cusp of the cone. So in presence of cosmic string, we have so-called deficit angle, which defines by the string linear density. The string linear density is the main string parameter, and deficit angle delta theta is the main parameter which very important in cosmic string search as gravitational lensing objects. Next, please. There are two main methods of cosmic string search. First is the analysis of anisotropy and polarization of CMB radiation, looking for spatial step-like discontinuities from the data of WMAP and Planck. And the second method is analysis of strong gravitational lensing effects by high-resolution optical instruments to look for excess of such events, of pairs of gravitational lensing objects. So-called new Milky Way of gravitational lenses due to cosmic string, and also to find the special isophot cuts which can produce cosmic string. Okay, next one, please. The current status of cosmic string, I'll briefly discuss here. Now we have strong restriction on the linear density of cosmic string. The first 2 points indicated here are in fact represent in fact one strategy to analyze the cumulative contribution of the string network to the total energy of the universe. In this approach, model of the cosmic string network is characterized by the function of its own stress energy tensor from simulations. And then this function is incorporated in the simulation of the CMB anisotropy. And finally, the common simulated CMB spectra are optimized under cosmological parameters, including, of course, the cosmic string network parameter. And finally, to be consistent with WMAP and Planck data. The cosmic string network simulation are always model dependent and based on observationally unverifiable initial initial conditions. And so it seems that string network model doesn't conform by Planck and WMAP data because the absence of observational evidence strongly indicate a very small number of cosmic strings in the universe, maybe only one or two. The next point focus on direct search for individual strings. Here there are several methods, for example, methods based on the assumption that the number density of cosmic string is approximately known. The next method, this is method of our group, is based on convolution with special filters. And also there are many works which used Kenny algorithm for future CMB experiments. As you can see, all these methods give the same order of restriction on cosmic string linear density, 10 to -7. Next slide, please. Okay, here I present possible observational cosmic string parameters. This is amplitude of cosmic string anisotropy, which can be present in the following form, depending on cosmic string linear density and on deficit angle, and also on string velocity. For example, about the orders of these effects, the cosmic string with amplitude 80 micro K will have deficit angle approximately 6 arc seconds. And the so-called light cosmic string with amplitude 1.5 macro K will have the deficit angle 0.1 arc seconds. Deficit angle indicates the separation between gravitational lensing pairs, which I discuss later. Okay, next slide, please. How we can search cosmic string signatures in CMB anisotropy? This is due to so-called Kaiser-Stebbins effect. In presence of string in conical space-time, due to simple Doppler effect, it is generated the special picture of CMB anisotropy. The hot spot and the cold spot separated by extremely one-dimensional cut. Next slide, please. Using the appropriate filter, which is shifted, next slide, please, and rotated, because we don't know the inclination of the real string. Next slide, please. We construct the map of one-dimensional string signatures. This is indicated in the bottom of the picture. Next slide, please. We used the modified Haar filter adapted for our purposes. It's usual Haar wavelet, but shifted. Okay, next, please. There are final results of convolution of Haar filter with Planck data for different string amplitudes. The most heavy string, which generates the anisotropy about 40 micro-K, is only one, indicated in red square. This is a strong argument against the network conception, because now we can see only one string. For lower amplitudes, there are, of course, many string candidates, but a lot of spurious signatures, wrong candidates as noise. The region near galactic equator and its boundary is a filter to remove the galactic contribution, and so the signatures near the galactic disk is also wrong candidates because it's due to the filter. Okay, we found one cosmic string candidates in radio data. Next slide, please. Small dashes indicate the gradient from the hot area to the cold area. This direction should be correlated. Next slide, please. To verify our cosmic string candidate, we have to make additional independent tests looking for gravitational lensing events in the region of our candidate. Of course, in the total scale, there are many extragalactic gravitational lenses object, I mean usual gravitational lens. But in the case of string, we have to have a statistically significant excess of such gravitational lensed pairs. Next slide, please. And so we are analyzed 31 field, 1 by 1 square degree. Next slide, please. Here I present an example of such a field with red circles. I indicate candidates to be gravitational lens images. Next slide, please. It's very important to know choose the criteria in searching of such pairs. First of all, the angular distance between the components have to be between 2 and 9 arc seconds. The lower limit comes from the resolution of the survey. We use SDSS survey, and the upper limits from the restriction to the linear density of cosmic string, because in opposite case, we can detect without any filter the cosmic string. It will be, if it will be very heavy, and so it produced very strong hot and cold spot and cold spot in CMB anisotropy. Also, we have to choose objects with stellar magnitude restricted to visual search. We produced the both researches, visual and automatical. The criteria for objects to have gravitational nature is the same redshifts and the same component intensity ratio in all available frequency bands. Next slide, please. This is an example in SDSS of one object. Next slide, please. So we used magnitudes uncertainties, and photometric redshift. Next slide, please. Next slide, please. Here I indicate how we calculated the errors of the difference of magnitudes, which is the same as the ratio of intensities. They have to be 0 for gravitational lensing objects with an errors. Next slide, please. There are some examples of gravitational lens pairs candidates in all these fields. Next slide, please. We found such candidates in the field of our cosmic string candidates, and we also found candidates of gravitational lensing pairs in so-called empty fields or control fields which do not contain any string in CMB data. And we compared two distribution of gravitational lensing pair. And the distribution according statistical analysis are different. So the distribution of gravitational lensing pairs in our cosmic string candidate field differs from the empty fields. Next slide, please. And finally, we found 3 sigma excess in string field of such pairs. Depending on angular separation, the most excess is for pairs with angular distance 8.5 arc seconds. Next slide, please. This is preliminary statistical result, but it's very important that we study the cosmic string candidate by 2 independent methods, by radio methods using Planck and WMAP data, and by optical methods, looking for an excess of gravitational lensing pairs in the region of these candidates. Of course, to confirm that we really are dealing with gravitational lens pairs, we need the spectra of these pairs, because now we compare only intensity in 5 bands from SDSS catalog. And the final proof that we are dealing with cosmic string will be high resolution images with special isopod cuts. Okay. As I told, for future work, we need more spectroscopic information for these candidates, but preliminary statistical results indicate that we have a single cosmic string in this field. Okay, thank you very much.
Okay, thank you, Olga.
Yes.
Question, please. It's possible to do the question directly.
One moment, please. Could you be so kind to repeat your questions? I lost the sound.
Okay. Question, please.
Mm-hmm. I see one question.
Yes.
one moment. Yeah, we modeled maps without string and with some cosmic string, and apply our Haar filter to these simulated maps. And so we can say that our method could recognize the strings from the random noise. Of course, this is only a statistical result, but could you show the 3 Mulvey projections on my slides?
What is the slide number? We can go back, but what is the slide number? Just stop me when you need.
See.
Before?
Next here. Thank you. No.
This
3 maps. Yeah, this one. So we can recognize the string on the map with the anisotropy, which is approximately 40 micro-K, but for light string, we have a lot of noisy, we have a lot of noise detection, and here we can recognize the strings with only some probability.
Okay. Other questions? You have a time? Take note. Thank you, Olga, for your speech. Thank you very, very much.
Thank you.
Okay. Next speaker, Maret Einasto. Connectivity and galaxy populations in supercluster cocoons, the case of A2142. Thank you.
Здравствуйте. 15-20 сначала. Ну, я открою. Сейчас, подождите.
Hello, can you see me? And can you hear me?
Yes, we see and we hear.
Okay, I will. And can you see me now? Because if I enter, full screen, I cannot see all the slides by myself. Anyway, to start with, I would like to thank the organizers for this wonderful meeting. And I seem to be the only one who is talking about superclusters in this meeting. So let's start. In my first introductory slide, I show an image from the Sloan Digital Sky Survey. And this is image from central part of which galaxy cluster Abel 2142, which is the main cluster of our supercluster under study. And this is the reason why I show this image. And those galaxies are the 2 brightest galaxies in the supercluster. Now we all know that the most remarkable pattern in the universe is the cosmic web, the network of galaxies, groups, and clusters of galaxies which are connected by filaments and separated by voids. And this cosmic web has evolved from tiny density fluctuations measured by CEDM, measurements. And here is a blank picture of the cosmic microwave background. And the cosmic wave as seen in the luminosity density field of the Sloan Digital Sky Survey. And today in the first talk, Jaan Einasto very shortly outlined the discovery story of the cosmic wave. And I only add to this that the first international conference dedicated to the large-scale structure of the universe in its present meaning was held in Tallinn in 1978, and it was organized by Tartu Observatory astronomers together with Jakob Sedlowitz and his group. In the cosmic wave, superclusters are the largest systems. They consist of galaxies, galaxy clusters, which are connected by filaments, and between two neighboring superclusters, there are voids, empty regions where there is no visible galaxy. If we would have velocity field data for the all galaxies, as we have for the local galaxies, for the local universe, we have cosmic flow data, then we could see that in the cosmic velocity field, galaxy velocities are pointed towards central paths or high density regions. All those regions can be called as regions of dynamical influence of a supercluster. And this is the picture of our local Laniakea supercluster as it was presented and analyzed by Brent Tully and his group, so that all the velocities are pointed towards high-density central part of the supercluster. And here, somewhere in the void, there is kind of watershed where velocities from one side, they point towards one supercluster, and from another side towards another supercluster. In this picture, this is Perseus supercluster. And so that this border is like the border of regions of dynamical influence or basins in Tully's study. Brent Tully and his group called as supercluster everything what is within this border. But to keep the term supercluster in its traditional meaning as high global density region, Einasto and others recently proposed to name this low density region around superclusters as cocoons. And so the whole cosmic wave can be divided between cocoons of different superclusters. Now getting closer to Abel 2142. This is again the Sloan image, but each sphere in this plot represents galaxy group in the Sloan. And with different colors, I highlighted members of some prominent superclusters, like the Sloan Great Wall here, the Corona Borealis supercluster here, and here next to it, next bright supercluster is Abel 2142, which is named after its brightest cluster. Now, why this supercluster is interesting? First of all, it catched our attention because at this cluster, in the slow luminosity density field, there is the highest luminosity. And this is because this cluster itself is very, very luminous and rich, and actually more luminous and rich than, for example, the richest clusters in the Sloan Great Wall, which are approximately at the same distance. Then next interesting feature is that in our study of supercluster morphology for large number of superclusters, we found that this supercluster has almost spherical main body, which is very unusual because rich superclusters typically have elongated main bodies. And then also this supercluster in its main body has only one very rich cluster. And this is also unusual because rich superclusters usually have several rich clusters in them. And then if we plot, here I do not show individual galaxy groups in the supercluster, but all the rich galaxy groups in the supercluster are located along a straight tail, which forms supercluster axis. And this is also unusual because straight structures are not typical in the cosmic web, or just opposite. All the structures are somewhat curved or have some whatever shape, but they are not straight. So that those were the reasons why we started to study this supercluster. And here in this plot, I show sky distribution of galaxies in the supercluster. They are color-coded according to the value of luminosity density. This is red and yellow correspond to supercluster, and green, blue, and black to low-density region around it. And cocoon borders are marked with the lowest density regions around the supercluster. And this correlates, density field correlates with velocity field. We, of course, do not have velocity data for those galaxies, but approximately those borders agree with minimum in the velocity field. In our study, we used data from Sloan Digital Sky Survey, supercluster catalog based on luminosity density field by Liivamägi et al., and group and filament catalogs by Tempel et al. Now a bit more detailed about the structure of the supercluster. As I already mentioned, it has almost spherical main body. But within that main body, we found that there is high density core, which is the sky distribution of galaxies in it also is shown here. And this is centered at the cluster Abel 2142 with some substructures connected to it and with nearby groups. And in the sky distribution, this high density core is surrounded by a minimum in galaxy distribution where there is almost no visible galaxies. But still it is the central part of the main body. Then it is surrounded by lower density outskirts regions of the supercluster, and finally cocoon. And this is, I am showing this because this is the basic structure of rich superclusters. And very rich superclusters typically may have several high density cores, and typically those high density cores in rich superclusters contain several rich clusters. And altogether, for example, in the Seppi supercluster, which is the richest system in the nearby universe, there is over 30 rich clusters. And in this one, there is only one. So that, as I told, by its structure is this, from one side it is typical, but from the other side there are very unusual features. And also poor superclusters typically do not have such high density cores. Now, this was about the overall structure of the supercluster, but we also looked at filaments inside the supercluster and around it. And what we found that basically the supercluster itself is populated by small, short filaments, but there are 6 long filaments extending out of the supercluster main body. which makes connectivity of the supercluster equal to 6. But what is very interesting, actually, if we look at galaxies in those long filaments, then the nearest one, the supercluster center, they are approximately at the borders of the main body of the supercluster. And here those long filaments end, and the main body itself is surrounded by short filaments only, so that those long filaments are disconnected from the supercluster main body. And here maybe the most interesting what we found was that there is one long filament which starts in the supercluster tail, and extends out up to the lowest density end at cocoon border. And we can draw a straight line along the supercluster axis, which continues at this filament. So altogether, they form the longest striped structure in the universe discovered so far. And this is at least 75 megaparsec long. Now a bit more details about the supercluster high density core. I show again the distribution of galaxies in the high density core, and different colors show galaxies in different structures. The main cluster itself, its substructures, and nearby groups. In the phase space diagram, here this is the distance from cluster center, projected distance, and velocity difference between galaxies and cluster center. Simulations show that in such type of diagrams, those galaxies which have been in the cluster already for a long time, or so-called early info region. This is here in this part of the diagram, and galaxies which are now falling in are in this part of the diagram. And this between 0.5 and 2 megaparsec, there is this info region for the main cluster, shown also here. We see that all the structures around the cluster are falling in into the cluster, and this is this minimum or border of the high density core. This means that that connectivity of this high density core is 6 or 7, it depends slightly on group definition, and it is detached from the supercluster main body. If all those structures are falling into the cluster, then maybe this high density core is already collapsing. And we can check this if we compare distribution of galaxies, or actually the mass distribution in the supercluster with spherical collapse model. In the spherical collapse model, the evolution of spherical perturbation can be characterized with specific moments, which each have typical density contrast. And first of them is turnaround, at which spherical perturbation stops expanding and starts to collapse. And for standard cosmological model with omega lambda 0.26, this density contrast is approximately 30. Then if density contrast is not large enough to collapse now, then maybe the perturbation may collapse in the future, but density contrast has to be above 8 for that. And there is also zero gravity zone where gravity of the system equals anti-gravity, and with density contrast above 5, and linear, and also linear regime where density contrast is 1, and this approximately agrees with cocoon border. Now, to find those density contrast, we had to calculate mass distribution, and from mass distribution we can find density contrast distribution for the supercluster. And for mass estimates, we use dynamical masses of groups from Temple et al. Group catalog. So that I show this density contrast curve for the supercluster here. This is distance from the supercluster center and density contrast. Here, this is the border of the high density core of the supercluster. And we see that density contrast here is much higher than needed for turnaround. It's around 30, this zone here in the sky distribution. So that this shows that this high density core has started to collapse already long time ago. And now is in the process of realization. And from different mass estimates, substructure analysis of the cluster and also from the analysis of galaxy populations, we propose that this high density core started to collapse at least 4 gigayears ago. This corresponds to redshift 0.5. And this is very interesting epoch in the structure evolution, because according to current cosmological paradigm, this is the epoch where dark energy started to take over, or started the influence started to feel. Now, this turnaround density contrast actually approximately corresponds to scale 8 megaparsec, which surrounds the supercluster main body. And zero gravity zone surrounds the whole main body. Here. Which is so that from those calculations, we can conclude, we can assume that all the main body of the supercluster already has started to collapse. And this may be the reason why exactly at the same region, those long filaments are destroyed and supercluster is only surrounded by short filaments. So maybe they are destroyed because of the processes during collapse. And also in the supercluster tail, there are several merging group pairs which may form individual systems in the future, so that the whole supercluster will split into several subsystems. What I also would like to say is that those density contrast values are for omega m equal 0.27 for our standard model. But now, as we heard also in this conference, some observations like kilodegree survey, they hint that it might be possible that omega m actually has higher value. And in that case, the density contrast for the turnaround has lower value, is somewhat around 8, like future collapse here. And if omega m has higher value, then this larger region is already collapsing. And if we use mass estimates and structure analysis and the analysis of filaments around the supercluster, then altogether we can maybe estimate more precisely the size of collapsing region, and it may be also be test for the cosmology. And I mentioned that this is the first this kind of study, so only the first step in this way. And in one slide, I show multi-wavelength view of Abel 2142. This is in radio halo. The size of this is in the center of the cluster, approximately here. X-ray halo, blank map, and also the brightest galaxies. And what is interesting, they are all elongated and aligned with the supercluster axis, which hints that the supercluster axis acts as a main axis for merging and infall in this supercluster. Now my time is soon over, but shortly about galaxy populations. I only show I only talk about galaxies with basically focus on TN4000 parameter, which can be a spectral parameter which characterizes ages of stellar populations or the time which passed from the last star formation event. Galaxies with high value of T4000 parameter are quenched and have very old stellar populations. Galaxies with low value of this parameter are still star forming. And this shows this map of this is distance from the cluster center and the 4000 parameter for the high density core of the supercluster. And we see that the central part is early infant region of the cluster is all populated with galaxies with very old stellar populations. And it is very reasonable because when galaxies fall into cluster, this is the early infant region, they have been in the cluster already for a long time, have time to orbit here and lose their gas by various processes which are at work at those extreme environments of high density cores of clusters. But here also we see that infouling groups have galaxies with very old stellar populations, and this is called preprocessing. But anyway, we can assume that galaxies with such old stellar populations are characteristics to central parts of galaxy clusters and groups. And when we looked at galaxy properties in cocoon, we thought that we do not find such galaxies there. But it is just the opposite. Many galaxies in very poor groups and even single galaxies in cocoon region also have very old stellar populations. This may be a problem for galaxy evolution models. And now short summary of my talk. I showed that high density cores of superclusters are the largest objects in the universe which may collapse either now or in the future, and their properties can be used to constrain cosmological models. And also the presence of very straight structures in the universe. Is this just a curious fact or also can be used as test for the cosmological model? And also our results about galaxy populations may also present some challenge for galaxy evolution models. So summarizing, we can use superclusters as test objects for several aspects in cosmology. Okay, and since we have cocoon, we should also have a butterfly. Thank you. And on my last slide, I thank all my co-authors. And that's it.
Thank you, Maret. Question, please?
I try to go back to meeting screen.
Kirill, please.
I can.
Maret, excuse me, it's Gregory Vereshchagin speaking. Just a curiosity, this linear structure you showed us of 75H megaparsec, could this be just a projection effect? And I mean, we are looking on edge to the system and it should be just curved structure somehow, but we are looking at, I mean, our projection effect is that, and also the size. It could be longer possibly than 75 megaparsecs, but again, projection tells us about the size.
I have to answer no to both questions because I forgot to mention that when we look at galaxy velocities, I mean, we have redshift data, of course, but they are all in very narrow interval. So that all those galaxies are almost at the same distance. There is some trend along this straight structure so that it is slightly inclined, but it is not curved. And I should have shown this plot also, but well, so that it is not curved. And then it ends from, it has one endpoint here, and already the very last galaxy in this filament is slightly misplaced. But this is only one galaxy. But then there is this very low density region where this filament is has end. And also in the other end of the supercluster axis, this also ends, and it there is a void region and low density region. So that was it.
Very impressive. Thank you.
I remember you had two questions, and I thought that I have answered to both is no, but I forgot the second question.
Yes, actually you did. Both were about the projection effect.
Sorry.
Thank you.
One question, maybe from my side. Very impressive research, and I wanted to ask whether you know of any mechanism to hold the spherical collapse in the model as you presented it of the supercluster region. So, is there any way to stop the onset of the collapse? Or is the only way for its outcome a formation of some giant-sized black hole?
Oh, if you say giant, I think even the largest black holes are much just different order, because here we are speaking about the whole, not only a cluster but the whole supercluster, and this typical size, the whole diameter of this collapsing body is say 25, 26 megaparsecs. It's very, very large. But there, let's say it may be that something is really wrong with our mass estimates. This is the crucial thing here. And well, when I go back I show this density contrast line, those are mass errors. Here in the central part, mass errors are so small because this is dominated by the cluster Abel 2142 itself. And we compared mass estimates from our catalog, from our data, and from X-ray data. And they practically coincided. There is difference was only 4%, which is incredible. But those mass errors may be larger. And so we don't know exactly the very precisely the size of this possibly collapsing core. And for this supercluster, for example, this means that there, at the border of this main body where tail starts, there is a pair of groups. And we cannot say whether they will fall into cluster and join it or they will separate. And this is the reason why I emphasized that to estimate those sizes of collapsing bodies, it is important to use some other information, like in our case, this connection of filaments. Did I answer your question?
Yes, thank you. Thank you.
Thank you.
Simonetta, we cannot hear you. There is a problem with your microphone. Simonetta, excuse me.
Yes.
We cannot hear you. Okay, please.
Okay. Can you hear me?
Yes.
Yes. Okay. Last speaker, Elena Panko, Substructures, the galaxy clusters in rich regions. Please, Elena.
Yes, I'm here. Good day. Thank you so much for the possibility to be at this meeting and to finish this brilliant section. My presentation is substructures in the galaxy clusters in rich regions. Oh, sorry. Yes. This is my young team in alphabet order. Svetlana Sarkisian, Valery Korshunov, Anton Sergeyeva, and our common results. The reasons for present study. From numerical simulation, we see the distribution of nodes inside the filaments, and we try to see it in real space. Another simulation, we see again this great node and small subhalos, and we can try to find it in real observations. Last gadget for simulation is the same situation. We must see some bright objects inside the filaments. More, the orientation of the bright galaxies, we hope must be to nearest objects. In reality, we see the same situation. For example, a row of your Dietrich and for this foremost cluster. Thank you, Piero Rosati, and his presentation about our observational data. We have a catalog of galaxy clusters with list of galaxies in each cluster field. Here we see the field in the same field in our using our tool. We see the galaxies, and here we see galaxies and galaxies background and stars. So first task was the assumed morphological types for each cluster from our list. But we can use both Morgan schema, Rosati schema, and other schemas, and we conclude that we can use common schema with such a version. More. The schema allows to assume the evolutionary stage of each cluster according to concentration and distribution of galaxies in the cluster. Our tool. From list of galaxies, we can construct the map with distribution of galaxies and special orientation and size of galaxies. Note, the size of galaxies here are not real sizes. Each symbol have the size according to our some adapted magnitude, but we can use real sizes from Suntory. It will be on the points. And our approach allows to analyze the distribution of galaxies inside the cluster. For example, we see the concentration, strong concentration of the center. Here you see the concentration versus some preferential diameter inside the cluster. And first results we obtained some years ago. Concentrated cluster with some linear substructure. It's the same situation we see in the X-rays main galaxy cluster. Here, another galaxies here, and bright open gas between this point and this point. Our dataset for present study. A lot of rich galaxy clusters. You can see mainly in most regions, and about 100 galaxy clusters, which form superclusters. Let's examine morphological types for each clusters, and in some of clusters we found X-type or epic types, peculiarities, process and process. Progress formed by galaxies, short chains of galaxies. And summary about 20% of the galaxy clusters have such peculiarities. The typical situation, cross peculiarity, two distributions of each line, and the number of stage is a number of bands of zones in which we constructed histograms. The main galaxy, brighted galaxy, alignment along the main band. The second one, concentrated cluster, and here the main galaxy, brighted galaxy, placed in the center, orientated along the second band. And we found a lot of such clusters which differ in forms of the bands. Especially here, we see compact chain with forward bands. And the next type process. Here, and here, and all situations are statistically significant. So interesting moment. We find the chain of galaxies with strong orientation to the nearest galaxy. So, like to Maret chain, but I have some interest moment because only two galaxies, here and here, orientated not to the nearest galaxy. We want to learn our alignment of galaxies in the perpendicular direction of main line here and here, and parallel direction to the main line. The also interesting case for supercluster, we have orientation main band to the nearest cluster, main band to one nearest cluster, and secondary band oriented to the farthest cluster in the supercluster. Okay, worst case correspond to position galaxies or in a sheet like here, or in a filament like here. In summary, I remember I had 15 minutes. We found more than 20 galaxies clusters in our dataset have specific significant level of peculiarities besides the linear substructures. We found different kinds of peculiarities, such as process, semi-process, short chain, or denser bands, We found invariant element of galaxies in the peculiarities correspond to cases of three-dimensional structures. And we show the regular peculiarities are not a certain case in distributional quantities. We can consider the presence of regular peculiarities as evaluation moment in a post-cluster formation. Thank you. Question, comments?
Thank you.
I'll get to see here.
Any
I'm
questions?
sorry.
May I ask, at first,
We are tired.
well, can you hear me? At first, thank you for a very interesting talk. But my question is, if you have clusters with such interesting substructures, could it be possible that actually you have a collection of closed groups instead of a cluster?
I'm sorry, repeat this.
Is it possible that those clusters with complex substructures, is it possible that they are actually a collection of closed galaxy groups and not a cluster?
Yes, it is possible, but we must to check it because our base data is two-dimensional catalog of galaxies. So we sometimes have two farthest and nearest clusters. It is possible.
So that you don't know how much they are contaminated by projections? Or you don't have redshift information?
We try to assume redshifts for different clusters, and we use in our work mathematical redshifts. Measured redshifts have only about 40% of our clusters with richness Storm 100.
Okay, thank you. But can you obtain redshifts from some existing service if they are overlapping?
That's right.
If your data are overlapping with some existing redshift service, can you obtain redshift from there?
I hope.
Okay, yes, I see. But again, thank you. It's very interesting.
Thank you. Thank you so much.
Okay. Thank you, Elena. This session is finished. I thanks to all the speakers on the large scale structure of the universe. It has been a truly inspiring moment. You have shared your deep knowledge and scientific results from the fractal network of galaxies, the biasing phenomenon, the powerful and promising cosmography by cluster long lensing, the progress of cosmology with the hypertelescope in lunar crater, the optical analysis of CMB cosmic string candidate, the interesting case of A2142 supercluster, and finally, the super substructures in the galaxy clusters in rich regions. Thank you very much for participating. And finally, I invite you, if you can, to participate to the other session of the meeting. Here in the chat, I write down the web link to give a look of the program. Thank you very much.